Welcome everyone. What I want to do in this short video is to present the course on complex dynamic systems that I give for the master course in applied mathematics at the Department of Information Engineering and Mathematics of the University of Siena. The course presents some introductory items on the concept of complex systems that are systems composed by many elements interacting in a nonlinear way. So finally, we can have a compact description of some properties of these systems by means of ordinary differential equations having a nonlinear right-hand side part. As you can understand easily, to have exact solutions of nonlinear ordinary differential equations can be very difficult. And so what we focus on is in the course is not to find the solutions, but analyze the system as a whole. And to do that, we focus on some tools that allow us to perform qualitative analysis of the system, which consists specifically with analyzing the stability of the steady states. The analysis of steady states can be done by using the linearization theorems, except when you have at least one eigenvalue of the linear approximation having a null real part. Unfortunately, in that cases, we cannot use a linearization, and so we must use different tools to tackle the properties of the system. And specifically, what I do in the course is to introduce the concept of bifurcations. Bifurcations are inducing the drastic changes in the geometry of the phase space of nonlinear systems. Thus, in that cases, you can observe the onset or disappearance of steady states, as well as change in the stability of the same states. Moreover, you can also observe the onset of oscillations, of stable oscillations also, consistent with limit cycles and attractive limit cycles in the phase space, which represent a system that are living out of the equilibrium, but without diverging to infinity. So they remain confined, and you can easily understand that these kind of systems are ubiquitous in our life, starting from biological systems to economic and social, and also, like I would say, geological and weather systems. So I will present a lot of examples of oscillating situations. And moreover, I will also introduce the concept of aperiodic oscillations in dynamic systems described by ordinary differential equations. So without any external noise or external disturbance or external stochastic factor influencing the dynamics. So we show that nonlinear systems can also behave aperiodically under the effect of internal mechanisms, and the aperiodic behavior is called deterministic chaos. And deterministic chaos is represents a dynamics which is sensitive to initial conditions, thus meaning that a tiny change in the initial conditions will produce eventually a large change in the asymptotic dynamics. So we will focus on the examples on some examples, well-known examples, and also real life examples of this behavior, and um, and we can also find some tools useful for solving the equations that are typical of the game theory. This course has some interactions also with the other courses I give in the same master course on game theory. And finally, what I would like to say is that the exam for the students can be done in two ways, or in a standard way where you have a written part and the oral part, concerning respectively the practical part like exercises and model simulations, and the theoretical part, which will be checked in the oral part of the exam. And alternatively, students can also ask for developing quite research projects, and in this case, we can work together with the students in groups or separately, by trying to solve some research questions, to answer some research questions that I'm working currently in this field together with my group. So I thank you very much for your attention, and bye bye.